Ladies and gentlemen, let's continue with chapter 8 on internal forced convection out of the textbook of Cengel and Ghajar. We did all the theory in this chapter, which was firstly an average velocity and temperature, the entrance region, the general thermal analysis, laminar flowing tubes, and turbulent flowing tubes. With the previous lecture, I've just shown you some of the equations which can be used if you've got turbulent flow through tubes. And what we're going to do in this lecture and in the next lecture is I'm going to do a few more examples so that you could understand the theory a little bit better. So the example that I'm going to do is now an example where we've got a constant heat flux. The previous example was an example where the wall temperature was constant. It was constant because we had condensation on the outside wall. In this case, this tube is being electrically heated. And you can do it by coiling a wire around it with a high thermal resistance, or you can, if it's maybe a stainless steel tube, you can directly just put a current through it. So that is how you're going to get a constant heat flux. Now the tube diameter is 25 millimeters. It's water, inlet temperature of 20 degrees. The volume flow rate is 12 liters per minute. And the tube length, I forgot to put that in, is 6 meters. 6 meters in length. The outlet temperature is 80 degrees Celsius. The question is to determine the wall temperature of the tube at the outlet. What will the wall temperature be at the outlet so that the water temperature is equal to 80 degrees Celsius? Very important, I always recommend that you make a sketch. And if you look at this problem, our water temperature is going to be, inlet is 20, and the outlet temperature is going to be 80. Okay. Now, because it's a constant heat flux problem, if you go and look in that paragraph that I've said is so important, you will see that for a constant heat flux, the fluid temperature will increase linearly because we put in the same amount of heat every millimeter, every 10 millimeters, 1 kilowatt, another kilowatt, another kilowatt. Therefore, the temperature of the water has to increase linearly. Okay, and for these types of problems, our wall temperature normally does something like that. Once the flow is fully developed. If it's developing, the heat transfer coefficient will be very high, and therefore the wall temperature's difference would be smaller until the flow is fully developed, and then you will have a constant delta T between the wall and the fluid. So it is very important to understand the theory of constant heat flux and a constant wall temperature, because you need that background to put the problem together and to really understand it and to make the right decisions. So with that, we can look at the bulk temperature of the water, which is going to be 20 plus 80 divided by 2. 20 the inlet temperature, 80 the outlet temperature, so that is 100 divided by 2 is at 50 degrees Celsius. At 50 degrees Celsius in table A9, you should know this table very well by now. Table A9, at a temperature of 50 degrees Celsius, we can get the density of the water as 988.1 kilograms per cubic meters. The thermal conductivity K is equal to 0.644 watts per meter Kelvin. The Cp value is equal to 4181 joules per kilogram Kelvin, and the Prandtl number is equal to 3.55. And the last one that we're going to need is the viscosity, 0.504 multiplied by 10 to the minus 3 kilograms per meter second. So the water at the bulk temperature, in this case, we do not have to guess. We've got the inlet temperature, the outlet temperature, 20 plus 80 divided by 2. So we get the properties at the temperature of 50. In table A9, the density 988.1, thermal conductivity 0.644, the CP 4181, the Prandtl 3.55, and the viscosity 0.504 multiplied by 10 to the minus 3. Normally, after you've done many of these examples, you will just immediately know that there are things which are more important than others. In this case, the volume flow rate has been given. It's not always handy to get the mass flow rate. So the mass flow rate is equal to the density multiplied by the volume flow rate. The density of the water is 988.1, and the volume flow rate is 0.012 cubic meters, and it is per minute, so we have to divide by 60, and the result is a mass flow rate of 0.1976 kilograms per second. We are also going to use two areas, and I'm going to work it out now, and that is firstly the cross-sectional area of the tube. So it is the wrong place. It is this area through which the water flows, which is going to be pi divided by 4 multiplied by 0.025 square, and that is going to be equal to 0.004909 square meters. And then the other area is the area for the heat transfer, and that would be the outside area of this tube, which would be equal to pi d multiplied by L. Pi, the diameter of the tube is 1 inch or 25 millimeters. The length is 6 meters, has been given. So the area for heat transfer is equal to 0.4712 square meters. We've got the inlet temperature, we've got the outlet temperature, we have the mass flow rate, and we've got the CP. So it is very easy to determine the heat transfer rate, which is equal to the mass flow rate, the CP, multiplied by the outlet temperature minus the inlet temperature. The mass flow rate we have determined is equal to 0.1976 multiplied by CP, which is 4181, multiplied by the temperature difference, 80 minus 20, and the result is a heat transfer rate of 49.6 kilowatts. Okay, now we've got the heat transfer rate. Again, if you've done many of these problems, you will know that one of the most important things to determine before the time is to know if the flow is laminar or turbulent. And for that, we need the Reynolds number. So the Reynolds number, usually in terms of equations, is equal to rho Vd divided by the viscosity. We do not have the velocity at this stage, but I've indicated to you that for a circular tube, take note, for a circular tube, you can write also the Reynolds number as 4 times the mass flow rate divided by the viscosity pi d. I hope you remember that. Okay. This is a very handy one to use. It's a simple derivation to get to that equation, but with that we can determine the Reynolds number as 4 times 0.1976 divided by 0.504 multiplied by 10 to the minus 3 pi divided by 0.3, and that gives us a Reynolds number of 15,480. 15,480. For a tube, the critical transition Reynolds number is about 2,100 to 2,300. At the Reynolds number of 10,000, the flow would be turbulent. So we can say that we know for sure that the flow would be turbulent through this tube. Question? Oh, sorry. Thank you. 0.025. Thank you. Okay. Now, it is not necessary that you calculate the Reynolds number directly like that. You could have first go and calculate the velocity. You can calculate the velocity from the volume flow rate, which is equal to the average velocity multiplied by the cross-sectional area. The volume flow rate is 0.012 divided by 60 is equal to the velocity multiplied by the cross-sectional area, 0.0004909. And from that you can get the velocity as 0.4074. Okay. And by putting it into that velocity, getting the viscosity here, you could have also calculated the Reynolds number like that. I see there's a question. No question. You're right. Okay? Okay. So the flow is turbulent. If we just go back to yesterday to the PowerPoint that I've showed to you, if we can just look at it again, you'll see that I've given you some equations for turbulent flow. Okay. We can see the friction factor. There's the Chilton-Colburn analogy equation, the Colburn equation, etc., up to the Glinsky equation. The first ones are the simplest ones to work out. The other ones you need to do much more work, but they are more accurate. But in general, these equations plus or minus 20% in terms of accuracy. So I'm lazy, so what I'm going to do is I'm going to say, let's calculate the Nusselt number as equal to 0.023, Reynolds to the 0.8, Prandtl to the n. It's almost the simplest of all the equations available. Okay. And n, take note, n is equal to 0.3 for cooling applications, and n is equal to 0.4 if we've got a heating application. So the fluid is being heated, so n must be equal to 0.4. So therefore, if we go and calculate the Nusselt number, it is equal to 0.023. Reynolds number is 15,480 to the 0.8. The Prandtl is 3.55, and n is equal to 0.4. Because where they give us the equation, they say n is equal to 0.3 for cooling, n is equal to 0.4 for heating. If we calculate the Nusselt number, it is equal to 85.83. 85.83. The Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by K. It's 85.8. The heat transfer is what we need. The tube diameter is equal to 25 millimeters, divided by the thermal conductivity, which is equal to 0.644, is equal to 85.8, and that gives us a heat transfer coefficient of 2,211 watts per square meter degree Celsius. It is always important to think about the flow regime and the heat transfer coefficients. So if we come back to the sketch that I've showed to you in terms of the fully developed part, in which the heat transfer coefficient will be constant. For turbulent flow, it takes 10 diameters before the flow is fully developed. 10 diameters is 250 millimeters. Okay. So that distance is 250 millimeters. So in that 250 millimeters, the heat transfer coefficient will be higher than that value that we've determined there. So therefore, if we look at the heat transfer coefficient as a function of x, and this is 6 meters, so 6,000 millimeters, 250 millimeters on this scale is something like that, 250, which means that the heat transfer coefficient would do something like that. And so for the first 250 millimeters, it will be higher than 2,211 watts per square meter degree Celsius. There are actually equations available in literature in which you can go and estimate that heat transfer coefficient. However, between friends, we will say, well, this is really negligible. For all practical purposes, we assume that the heat transfer coefficient is constant throughout the tube. Do you agree with me? Of course, for 5,750 millimeters, the heat transfer coefficient is the same. It is just changing over the first 250 millimeters. So it therefore means that if we look at this sketch of us, we can say that we are actually making the assumption that the heat transfer coefficient is constant all the way through, and we therefore have the following situation. That is our wall temperature of the tube. The question was to determine that temperature, but while we're busy with it, we are also going to determine it here at the center, here at 3 meters, because here at 3 meters, that temperature there is equal to 50 degrees Celsius. Okay. So 20, 50, and 80, we would like to know what is the wall temperature everywhere. Now that is now very easy to determine, because now we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the wall temperature E at the exit, TWE. Okay, TWE minus the fluid temperature. And the fluid temperature is the outlet temperature. So the heat transfer rate is equal to 49,575 is equal to the heat transfer coefficient, which is 2,211, multiplied by the surface area, which is equal to 0.4712, multiplied by the wall temperature at the outlet minus the water temperature at the outlet, which is 80 degrees. And from that, we can calculate the water temperature at the outlet is the wall temperature at the outlet must be equal to 127.6 degrees Celsius. Okay, so that temperature here is 127.6 degrees Celsius. We can go and do the same if we now want to determine the temperature here. The temperature of the wall at the bulk temperature, which is in the center of the tube. So we can write the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the wall temperature bulk minus the bulk temperature of the fluid. Everything is known except the wall temperature bulk, because that temperature there is equal to 50, the bulk temperature, and from that we can calculate that the wall temperature bulk is equal to 97.58 degrees Celsius. And if we are also interested in the inlet temperature of the wall, so that temperature there, the temperature of the wall at the inlet, we can also say the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area, the wall temperature at the inlet minus the inlet temperature. The inlet temperature is 20. All the other parameters stays the same, and we can calculate the wall temperature at the inlet as 67.58 degrees Celsius. Right, 67.58 degrees Celsius. What is different from the approach where we use a constant heat flux? Where we have a constant heat flux, that delta T is the same. So therefore, we can use this. If it was a constant surface temperature, we had to use the LMTD. Okay. Now let's suppose you actually forgot and you wanted to use the LMTD here. Okay. So if you do that, then you will have that temperature there and you will have that temperature there. Okay. So that temperature difference here would be equal to 127.6 minus 80, which is equal to 47.6 degrees Celsius. You agree? And here it would have been 67.58, and there it is 20. So this delta T here is also 47.6. Delta T's are the same. So if you would have now go and calculate the LMTD, this temperature difference, 47.6, minus this temperature difference, 47.6. Do you see the problem? Divided by the ln of 47.6 divided by 47.6. What is the ln of 1? The ln of 1? Is it 0? Yeah. So you've got 0 divided by 0. So you see it doesn't work in any case. It doesn't have to work because, because this has been developed for cases where our wall temperature is doing something like that and the other temperature is doing something like that. Here we can see that the delta T remains constant all the way. Here it doesn't, it changes. And we actually wanted to know what is a good average temperature difference, which would typically maybe be something like that. And that is actually what the LMTD means. That is why it is important that you really understand the two case studies very well when you do any problems. Ladies and gentlemen, any questions before we do another problem? Yep.
Just with the regards to the calculation of the Reynolds number using the velocity versus using the circular tube method, they give you different answers. They only differ by about 2 up and 2. Can we consider that an equal and then use either method?
They give you...
There's a difference in the answers.
In the answers?
Yeah.
Okay.
So, and then obviously that affects your Nusselt number, which affects your...
Yeah. How much is the difference?
It's only 202. Can we consider that negative?
Yes, so the question is, somebody did go and actually do these calculations and say there's a little bit of a difference in the Reynolds numbers. There shouldn't be. I think it must be a small calculation error because there's no really an assumption that was made there. If you go and look at, I hope I can do the derivation now, but it is the Reynolds number is equal to rho Vd divided by the viscosity. And then you can also say the mass flow rate is equal to rho multiplied by the area multiplied by the velocity. And this is equal to rho pi divided by 4 d squared multiplied by the velocity. So you can write this velocity as the mass flow rate divided by the rest, and you can put in you can substitute it in there, and then you should get that. Then you should get this equation. So we've done that derivation. However, remember, and that is now where I say this is important, ladies and gentlemen, you have to listen well. Okay, this equation. Previously, when we've derived it, I've put this next to it. Okay, so it is valid for a circular tube, but it is not valid if you've got a cross-sectional area like that, because then this is not correct, because this was obviously based on the circular tube, and that is then not going to work out. So it is going to work out for the circular cross-sectional area, but it is not going to work out for that one. But 99% of all the problems that we're going to do is normally circular. But just remember for those cases where it is not valid. Any more questions? Okay. Now let's suppose you would ask me, but you've used this very simple equation of Dittes and Boulter. You know, what about, let's suppose we want to be a little bit more accurate. Okay. We're going to redo the problem using the Glinsky equation. Okay. So if we redo the problem, so let's look at the Glinsky equation quickly before we start with it. If we can look at it. There it is. Okay. However, what do you see in the Glinsky equation? You will see we need the Reynolds number, the Prandtl number. We've got everything except the friction factor F. The friction factor F, okay? Now, previously, in the previous slide, I've actually summarized to you the friction factor. There you see it. An equation that you can use to determine it from. So there are two ways how we can get it. This is the friction factor as a function of Reynolds number. There is the results for laminar flow. Friction factor is 64 divided by Reynolds number. However, we are not in the laminar flow regime. We are at a Reynolds number of 15,480. So if you go and look on the Moody chart, there was one in your fluid mechanics textbook, but there's also one in this textbook, one of the appendices. So if you go and look at that, you will see that the friction factor is approximately equal to 0.03. So you can go directly from the Moody chart and go and determine the friction factor. The alternative is, more accurately, is to calculate the friction factor as equal to 0.790, the ln of the Reynolds number minus 1.64 to the minus 2. I think that's the Colebrook equation, something like that. And if you go and calculate it with that, it is equal to actually 0.2795. Not very easy to get from the Moody chart values which is accurate more than about one significant figure. However, what I always do is when I do something like that and I do the calculation, I just go and look at the graph quickly if it's about right, because it's very easy to make a mistake. So it's very easy to check. Right, now that we've got the friction factor, we can actually go and calculate the Nusselt number according to the Glinsky equation. That is the friction factor divided by 8. The Reynolds minus 1,000 multiplied by Prandtl divided by 1 plus 12.7. The friction factor divided by 8 to the 0.5 multiplied by Prandtl to the 2/3 minus 1. Okay. I'm not going to put in all the values for you because we've got the friction factor, there it is, the Reynolds number and the Prandtl number. You just need to do the substitution, and if you do that, you're going to calculate the Nusselt number as 89.97. 89.97. If we compare it to the previous Dieters-Boulter equation, you'll see that the error is about 6%. Okay, about 6%. And if you then go and calculate the heat transfer coefficient, then the heat transfer coefficient will be 2,318 watts per square meter degree Celsius. And if you then go and calculate the wall temperature at the exit, it would be equal to 125.4 degrees Celsius. 125.4, previously we've calculated it as 127.6. So you can see it's about right. Okay. And if you go and do the same with the other temperatures, it would be 95.39 degrees Celsius, and at the inlet it would be equal to 65.39 degrees Celsius. All the delta T's are the same. Okay, any questions? There's a question.
So which method is accurate?
Which method is accurate?
Yeah, if the answer is like 6%.
So in general, as a rule of thumb, the first equations were not as accurate as the latest equations. So if you go and look in the literature, when was the first one published and when the last one was published, then in general, the last equations in your textbook, the equation of Glinsky is the most accurate of all of them. Okay. Yep.
So with regards to when you read off the Moody chart, you just assume that the roughness of the path is
Sorry, I beg your pardon?
you assume the roughness of the path is 0 for smooth path.
Yes. Yeah. So this is a good question. The question was, I didn't show it, of course, all, but this is the Moody chart. But this is the lines for different surface roughnesses, epsilon divided by d values. And I've used this line, which is the line for a smooth tube. And actually, this equation is also for a smooth tube. Why did I do that? Well, I've done that because I myself, in our labs, we did go and measure actually typical tubes. What is the surface roughness? And if you go and measure it and you divide it by the diameter, for all practical purposes, it's smooth. So you get values typically, if you go and do measurements these days of hard-drawn or soft-drawn tubes, then typically it is 0.40 before you start getting your first value. Okay? This is if you measure it. In the old days, the tubes were casted, and they used sand on the inside. And those were actually at a stage called pipes and not tubes, because they were really rough. But these days it is almost impossible to get a rough tube. It's actually one of the experiments that we are busy with in our lab. We actually want to also do heat transfer coefficient experiments for rough tubes. And we actually find it very difficult to make the tubes rough, to get rough ones. Obviously, if there's scaling in industry, erosion or corrosion over a long period of time, then the surface roughness, the epsilon divided by d, can become significant. I'm going to come back to your question just now. The other case where the epsilon divided by d normally becomes significant is with very small tube diameter. So if you've got micro channels, so where the diameter starts becoming 1 millimeter and less, then this becomes more important. And then sort of, let's call it the same type of surface roughness that you will have in a macro tube, then the epsilon divided by d becomes significant. You've got another question?
When you work out your H value,
The heat transfer coefficient.
the debate was now that it was manageable, that it was so long. But if you had to use the LMTD method, technically the temperature that you
Yes.
the raw temperature would be slightly less.
Yes.
That the temperature, there would be a temperature.
Yes.
So then you could use the LMTD method.
You're going to, so the question was, if you take into consideration that actually that happens, the first part is developing, then you can actually go and use the LMTD. I think so. I think you can try it. Obviously, the value wouldn't be equal to 0 as now. However, as an engineer, just look at this, and you will see that the two lines needs to be parallel to each other because of the constant heat flux, and it's going to be over 5.75 meters. So therefore, the delta T is actually easiest to use and most accurate, because it is really what is actually happening. Okay. Any more questions? Yep.
I just want to ask, because the H value is so high in that first part, won't it make a big difference to calculate the temperature at the inlet using the delta T?
Yes. So the question was, the flow is developing, so the wall temperature that we calculate there, is it accurate? And the answer is no, it is not so accurate.
What's the error?
I don't know. As I've said, you can actually, there are equations where you can actually go and calculate that. I don't think it will be tenths of degrees. I don't think it will be that much. Okay. Heat transfer, you will see that answers plus or minus 20% is actually considered as quite accurate. Because all the correlations are just accurate with plus or minus 20%. There are very few which is more accurate than that. And specifically in the next chapter, we will address that also many times. What you're going to see is, remember, at this stage I told you that the material is going to be presented to you while we first do baby steps before we're going to start running. So we've started with convection heat transfer, and then external convection, internal convection. We're going to do the natural convection, and you've already done the radiation. And then at last we're going to get to the heat exchangers. And with the heat exchangers, we are always going to have these types of scenarios. And there, almost 100% of the cases, we always use the LMTD. Okay. Any more questions? Okay. Next problem. Next problem. Are you guys tired today? Okay, so the next problem is an air conditioning channel. Many of you are interested in air conditioning, and you did some vacation work at some of these companies. And this is typically an air conditioning channel, then a roof. Okay. And in this air conditioning channel, the chilled air temperature is 10 degrees Celsius, and the volume flow rate is equal to 0.15 cubic meters per second. The length of this duct is 40 meters, so it is quite long. Okay. And its geometry is 200 millimeters in that direction and 600 millimeters in that direction. So normally this length is smaller than that length. Why? Because in many of the spaces up in the roofs, there are limited space. Okay? Very limited space, especially in buildings where all the floors are casted. To put that air conditioning ducts in there, if that is maybe the wall there or the floor of the next level, then they put in a false ceiling in here, like that, and then the air conditioning duct will be there. So normally it will not be 600 in this direction and 200 in that direction, because then you do not use that 600 millimeters of space. Okay. So what I want you to do is go and calculate the outlet temperature. Okay. So the question is, determine the outlet temperature of this duct. Is it a very important problem? Yes, it is, because if you spend a lot of money to take air, maybe in this venue, cool it down to 10 degrees Celsius, and now you have to transport it through a duct of 40 meters before you can put it into the venue, this temperature increase is very important. You want it to be as low as possible. Okay. So in this case, the air temperature here can typically rise to 40 degrees. Now, if that is the case, then it is a good assumption to look at this problem and say, what type of problem is it? Is it a constant heat flux, or is it a constant wall temperature? It's a constant wall temperature problem. So it means that the surface temperature is equal to 40 degrees Celsius, and it is a problem where the wall temperature is constant. If that is the case, then again, a graph is a very good thing to have. Our inlet temperature is going to be 10, like that. Our wall temperature is going to be 40, 40 and 40. And when the air enters here, the temperature difference is going to be 30. So there's going to be lots of heat transfer. But as the air starts to heat, the temperature difference becomes smaller and smaller. So the temperature difference of the air is going to do something like that. And that is the outlet temperature, and that is what you have to determine. So we will not have enough time to go through this problem. So please go and try it at home. And then with the next lecture, I will also go through it. Thank you very much.